All right. So I'd like to start off each of our lectures this term from here on out by doing a sample problem, both as a review, as a warm-up for the class, but also because the more sample problems you get exposed to, when it comes to doing that super stressful midterm, you will have seen so many problems that you'll be like, wow, I've seen this before, this is easy. So you can take the next 3 or 4 minutes. We've got a function definition and then an application of it up at top, trying to evaluate that expression, that function call, on a piece of paper. So not using Racket, actually do it with a pen and paper. And then we'll see here in a minute how you've done. And you can work together, you don't have to be quiet or anything like that.
帮我做这个。
All right. So I see a number of you have actually taken a crack at solving this. So what is the first step that we would do to evaluate this? At the back, you're going to have to speak up.
Convert it into just a normal mathematical equation.
Convert it into a normal mathematical equation. How would we evaluate the Racket code, or evaluate the Racket code?
Find magic 1, 2, 3.
So we would first evaluate the argument magic 1, 2, 3. That is the answer. Functions in Racket can only be applied to values. And if you look at this function magic here, it's applied to a function, call, and an expression, and a value. So we're actually going to have to simplify the arguments before we can apply magic. So we're going to always look at the leftmost innermost to evaluate first. And that one is going to be this call here. Now looking at this call to magic, we see that its 3 arguments are already values. So we can apply it. We're going to make the substitutions directly into it. So when we're doing stepping on a piece of paper, it's important to remember 1 step per line, and that you should not use an equals. You should use the yields arrow. And yes, that is something that you could lose marks for on an exam, so it's important to keep that in mind. So the next step that we would have is we're going to replace magic 1, 2, 3 with the body of function magic 1, 2, 3, where the parameter values have been substituted in. So we end up with plus 1, 2. So that's our next line. What do we do next? What's the next step? Back?
Evaluate times 1, 2.
We're going to evaluate times 1, 2. That's exactly correct. Well, 2 times 1 is obviously 2. All right. What's the next step?
Go for 2 times 3.
2 times 3. Yep. So we're starting at the leftmost and working our way towards the right, evaluating each argument as we go. So we'll skip a few steps here. By that I mean I won't draw it out of you. The next step and then on that same note, but a new line, all right. What's next?
Add 2, 6, and 3.
We're going to add 2, 6, and 3. Just a heads up, you don't get a calculator in this course for your exams. All right, what comes after this step?
1 and 1.
Add the 1 and 1, yep. We're running out of space. All right, let's do it here. All right. Now we're down to magic being applied to values. So what do we do now? Let's go with a different person. At the back there, you're gonna have to speak up.
Basically start over again, evaluating magic with those numbers instead.
Yep, we're going to now, since magic's per arguments are all values, now we're going to substitute them into the body of magic. So in the next step, we're going to go, what do we got? 11 and 2, and then we've got 2 and 2, and let's put this on the next line. We've got 11 and 2. All right. Now, again, we've got arguments which are not values, so we're going to start evaluating from the leftmost argument, and I'll spare you having to drag that out of you, so let's just do this up here. So 11 times 2 is obviously 22. And again, you can only evaluate one of these per line. I know it's tempting to do it all in one line, but don't. Each one is a separate step. And we're done. Racket and functional programming languages, you can take a pen and a paper and you can completely evaluate the program on a piece of paper because you can trace through the steps. Get as much practice with this as you can because it'll be helpful not only for understanding your own code that you're writing, but it's also helpful for the exam when we say, hey, why don't you try one of these problems? 1 mark per line, kind of deal. All right, any questions about how we evaluated this? All right. So a couple announcements to make just to keep in mind. Make sure that you've got A0 handed in and you got 5 out of 5 from Marcus. I know A0's deadline I think is today. And if you've missed the deadline, get it in. If you don't get A0 submitted and correct, then you won't receive any marks for any other assignments until you do. So it's absolutely mission critical that you get assignment 0 done. And then you can get started on A1, of course. And A2 will be released end of the week as well for those of you who are ahead, which is great. All right, so let's turn this light off. What we're going to do now is start a new module, and that is module 3. And if you're following along with the slides, these are posted on the course website. They are not available in print. Just keep that in mind. So you're going to have to download them off the course website. And this module is called the design recipe. So we're not actually going to be really writing any code for this module. And for those of you who have had a friend in this course or taken 115 or taken 135 before, I imagine that this particular name, design recipe, is causing you to shiver in fear or groan in pain. And I'm hoping that by the end of today, that you have a bit better of an understanding as to why this exists and why we are asking you to do it. And for those of you who have never heard of it before, you have nothing to fear. There's no code, there's no math involved with it. All right, so if we look at a computer program, you can think of it as I am giving the computer some instructions to perform some task for me. So I distinctly remember that when I was taking a math course, it probably would have been over 15 years ago, and I wasn't quite sure if my derivation of a particular formula was correct. So I opened up, if memory serves me, it was Maple, and I wrote a little program to do the derivation for me to validate my own answer. Computers are great at helping us with all kinds of mundane tasks, from doing math to automating vacuuming. I have vacuum robots. They're great. They are programmed robots that are capable of figuring out the layout of my house and cleaning it. It's all computer code. It's great. But really, a computer program is a form of communication. It's communication between you issuing your computer some instructions. And in order for you to issue the computer some instructions, you have to use a very specific syntax. Because if you mess it up, the computer won't understand what you're doing. If you're trying to write Racket code and you write it in infix notation instead of postfix, Dr. Racket's going to be like, I don't know what this is. So it's very important with programs that we communicate effectively. Number one, so that the computer can understand what we are asking it to do. But what's even more important than just writing a correct program, we need to write programs that are readable. And that's something that I want to say comes with experience. But once you've had a negative experience with unreadable code, you'll understand very quickly why readability is so important and why having good communication skills around programming is so important. So let's say you are doing some big project. And let's suppose that project is, I don't know, you're trying to implement for a video game a mechanism to detect whether the arrow that you have fired hits the enemy. So you're trying to implement that code. All right. You start working on the code, and you're doing this as a side project, and then you realize, oh, I've got assignments in all 5 of my courses. So you go away for a week, and then midterms hit, so it's another week. And then you come back eventually, after final exams. Oh, I forgot I was writing this code. And you look at your code, and you're like, what is this shit? I know I was writing something to detect whether the arrow collided with the enemy, but I'm looking at this and I have no idea how I was doing that. You need to write readable code, number one, for yourself. Because as you are writing that code, you need to make sure that you can actually read it and understand what's going on. But it's not just for yourself now, it's for the future you. Because when you revisit that code some months in the future, you don't want to have to re-implement it simply because you can't understand what you wrote. And so many times people do this. If I'm in a hurry, I've had this happen. I was in a hurry, the paper deadline was coming up, and I was like, yeah, I'll just hash out this function real quick, and I did. I did no documentation. It wasn't readable. I didn't even write down what the parameters were supposed to be. Got the code to work, paper got accepted, forgot the code existed. Came back to it 4 years later. Oh, I need that function. I wrote that a few years ago. So I dug it up in my archive, I brought it out, and I looked at it, and I was like, what is this? I could not figure out what I had written 4 years ago. I hadn't documented it at all. So what did I end up doing? I rewrote the whole thing. What a waste of time. Not just wasting time me trying to understand something I had written before, but a waste of time for me to actually rewrite something I had technically already written. Writing readable code is very, very important. Now, what if I had given that code to somebody else? Would they have been able to understand it? Now, I know in this course you're not allowed to share code with each other, and please, please, please don't share code. That's how you get policy 71 and turn on to memes on Reddit. Don't share your code. But if you go out into industry, and whether that's you're going into like working for Google, or maybe you're going to work in some big physics lab, programming is pretty much everywhere these days. And you might have a coworker where they're going to share a program with you, or you're going to share a program with them. If your code isn't readable, then can you expect them to take your code and actually use it? If they take your code and then you go bugger off and do something else, and they're looking at, I don't know what I'm supposed to do here, then they're going to have to go bug you, and you might as well have done that task in the first place. So it's not just for you, it's for your coworkers. You need to be able to communicate what you are doing effectively with them. So your coworkers need it, your TAs want it as well. You need to make sure that you're being effective at communicating your program and your idea to the TAs so that they can actually grade your code. It's very, very important that your code is readable. And readability, it's very easy to believe that that's just about how you lay the code down in your file. So where do I put the open braces? Where do I put the closed braces? How much vertical and horizontal white spaces am I going to put? What am I going to name my function? What am I going to name my constants? What am I going to name the parameters? What indentation am I going to use? That's style, and that's very, very, very important. Believe me, if you come to my office for office hours and your code is written on one line, I will send you right back out the door until you fix it. I will not help anyone whose code is a mess. If you don't have indentation that's correct, I'll send you out the door. Now you might think that is unnecessarily cruel, but let me tell you this, 95% of the people who I sent out the door, they went and tidied up their code, did proper indenting, named their parameters properly, and in the process of doing so, they actually found their own bug. Their code was such a mess that they couldn't find their own bug. And when they fixed their code and made it look nice, they found the bug. So I'm not being cruel to you. 95% of you, if I do that to you, you will fix it. But that's only part of it. And by the way, all of this information about how you should style your code is available in the style guide, which is available on the course website. And whether you agree with it or not, you still are expected to use it. If you go to some company somewhere, they're going to hand you a style guide and you're expected to follow it, whether you like it or not. So we have a style guide. Please follow it. Don't lose marks for no reason. But there's more to it than that. Because I can write a really long function. I could write 25,000 lines of code, and I have written projects that are more lines than that. And I could have it perfectly indented and perfectly spaced, and every function perfectly named and parameters perfectly named, at least according to me. But that's not enough. Sometimes we actually like to add extra human-readable documentation to the code. For example, it's one thing to say that this function is, the name of the function is luminosity, compute luminosity. What about actually explaining what luminosity is so that other users will be able to say, oh, look, there's a function to compute luminosity. And here's a lovely text description of what luminosity is. We like to add extra documentation to our programs as notes to future selves or future developers so they can understand not only what this code is doing, but what it is for and what our thought process was when we were creating it. Maybe a particular parameter, there's no good name for it. And so we want to leave a note for ourselves and for future people to indicate, yeah, I know this parameter is called G, and that may not make any sense, but we actually mean the gravitational constant. Sorry, I'm not in physics. I don't know if that's actually the name. I haven't done physics since high school. So you can actually do this in most programming languages. You can leave behind documentation for people that is completely ignored by the computer, and we call these comments. And to indicate a comment, you use different symbols in each language. And in Racket, we use a semicolon. And the semicolon is going to indicate this is a comment. That means that Dr. Racket's going to ignore it. And you can put whatever you want in it. That line will be ignored. And in fact, if you want to know how I write programs for myself, all of this planning I talked about in previous lectures, I actually do it all as comments. So I write all of my comments, all of the documentation I write as comments. And then once I've completely planned out the program in comments, I come back and I fill the code in. And I don't have to add any extra documentation because it's already there. Comments are very important to creating readable code, and we do expect that you comment your code. Now, how you comment it, we have a very specific way that we want you to comment it, and you can add more comments on top of that, but there is a bare minimum that we want from you. Now, before we get into that, it's important to talk about good programs. Now, for the record, every programmer hates every other programmer's code. It's just a rule. You can give me your code and it doesn't matter if you were like Linus or Bill Gates or the Apple guy whose name I forgot. Yeah, I know I have an apple. It doesn't mean I like it. Anyways, it doesn't matter. They could give me their code, and I'm going to look at it and I'm going to say, ew, it's ugly. I don't like it. That's just a rule among programmers. Everybody hates everybody else's code. So we're not really judging that when we say good programs. But what does make a good program? It's a higher level idea. And we've got this list of words here, but I want to tell you about the most important things. Number one, it's important that it's readable. Whether or not you like the style of the code is one thing. Is the code readable? Yes or no? If it's readable, that's a good thing. Readability makes things like debugging easy because the code is easy to understand. And when it's easy to understand, it's easy to trace through, which means it's easy to find any little mistakes that have been made. Code that is readable is also code that's easy to maintain because we know exactly what the code does because the code was very forward about telling us what it's doing. Which means that another very important thing for a good program is maintainability. Whatever code you write needs to be able to be maintained. That means that it needs to be able to have bug fixes or being debugged easily. And if I decide at a later date to update the functionality of the code, that needs to be easy as well. So we want to write programs in such a way that they're easily maintainable. Now, what would that actually mean? Using constants. That's a way you can make your code maintainable. Because in graphics, I use the number pi all the time. But if I manually write out pi in each and every single one of my functions, I have not written maintainable code. Because if the value of pi changes, I have to go through all of my code base and manually fix it. And there's questions of, well, is this actually pi or is this some other magic number? I don't know. That's not maintainable. I can make my code maintainable by having constants. And then when an update to one of the constants values comes through, I make one change and it affects the whole world. That's maintainable code. And we're not just going to do that with constants. We do that with creating helper functions, which we'll talk more about next class. Now, another thing that's actually really important to create good code is efficiency. As it turns out, for many problems, there's more than one solution. For example, if you buy a frozen pizza, and I hope you haven't bought frozen pizza, there's better pizza out there, but suppose you did buy a frozen pizza. If you look on the box, it gives you different instructions for how to cook said frozen pizza. Now, one method for cooking the frozen pizza is to say, screw it and just eat it frozen. I'm sure there are people that have done that. Or you can put it in the microwave and it'll take like a minute. Or you can put it in the oven for like 45 minutes. There's always multiple ways to do things. And that is especially true in computer programming. But those methods some may take more time than others, and some may take more resources than others. For example, if I bake my pizza in an oven, sure, I get a pizza that I can eat, but it took 45 minutes, and ovens are not free to run. Whereas if I just eat the pizza frozen out of the box, it took no time and no resources. And I still got fed. Please don't eat frozen pizza, that's so gross. All right, same is true for computer programs. So for example, if I wanted to sort a list of things, say I wanted to sort you all by, I don't know, the first letter of your name. There are many different algorithms that we can actually use to sort. The worst being something like bubble sort, which it's very, very easy to implement, which is a good thing. But in terms of efficiency, how long it takes to perform the sort, it's really, really bad. One of the worst out there. It's not very efficient. Whereas there's other methods for sorting like merge sort that are significantly more efficient and take significantly less resources. When we are writing programs, we should always strive to produce a method that is as efficient as possible. Now, that might scare you. Thinking to yourself, I've never written code before. How do I know what I'm working on is efficient? We're not really expecting efficiency out of you in this course. If we were expecting efficiency out of you, this course would not be in Racket. It's not exactly efficient. Nobody is writing DNA sequencing, performance-driven code in Racket. Nobody is writing, massive first-person shooter games in Racket. That's ridiculous. We're not going to do that. So we're not going to care too much about efficiency here. But it is something that you should get some experience with. Because as you move on with programming, you'll start to see that, yes, some solutions are better than others. And when it comes to efficiency, I might have scared you into thinking, well, every time you go to solve an assignment problem, you're going to sit there, how do I make sure this is as fast as possible and as few instructions as possible or as few steps as possible? And if you can't come up with the solution right away, it's so tempting to get frustrated and anxious. Don't. You're new. We don't expect you to be perfect out of the box. It takes practice. You should always start with the solution you do know, regardless of how inefficient it is. And then work your way towards improving things. Start with what you can do, and then ask yourself, can I improve this? What are the weak points of what I have done? So we've got readability, maintainability, efficiency, and in my opinion, the last most important thing is making your programs generic or reusable. So in computer graphics, we use a lot of functions common to many different problems, and for me, one of them is a calculation known as luminosity. And what it is every pixel, every color pixel has a red component, a green component, and a blue component. And sometimes I don't want to deal with an image in color, I want to deal with it in grayscale. And there's many different ways you can convert it from full color to black and white. But the method that I prefer to use is this conversion to luminosity. And there's a very specific formula for that. So I may write for one function that takes an image and turns it into a Monet painting, a luminosity function there. And then a few months later, I'm working on S3D images, and I'm trying to turn them into comic book, except 3D. And I need luminosity again there, so I rewrite the luminosity function. And then I need it for something else, and something else, and for each of my 300 programs, I write a brand new luminosity conversion function. That doesn't make sense. If you see code that is being repeated within your own program or across multiple programs, that's a sign that that code, that little bit of code, should be reusable. Make it a function that's available to everybody. Make it a library function. All those built-in functions in Dr. Racket, like max and min and quotient and remainder, that's a library of common functions that Racket is providing to you, so you don't have to implement them yourself. Make your code reusable. Make it useful. Make it work in many different programs, not just the one that you were working on. Nobody wants to have to write code again. And that's a common mistake people make on their first work terms, is they get out there and their boss says, make me this thing. And you're like, yeah, I learned how to do this in my CS course. I'm going to make you that thing. And you make it from scratch, and it takes you 2 whole months to do it. And your boss comes back after 2 months, he's like, why did this take you 2 months? You could have gone online and downloaded it. It was a part of the basic C library. Reusability is super important. Not just for you to make your own code reusable, but for you to realize that some things are done already, and maybe it makes sense to use an existing implementation instead of doing it yourself. Now, obviously, the CS course, we want you to do it yourself. That's the whole point. But in the real world, that's how you have. All right. So, we kind of have an idea of what good programs look like. We understand that programs have to be readable and that they need to contain a lot of documentation. And I've talked a lot before about doing all of your planning for a program in advance. And you might just think that's just this crazy person at the front of the room rambling on about her coding life. No, actually, this is not just how I do it. This is how everybody does it, or at least everybody is supposed to be doing it. Everybody plans the program in advance. And how this is done really depends on where you are, whether you're taking this course, whether you're at a company, whether you're a software engineer. But there's this thing called a software requirement specification. And it's a massive document where you go out and you specify everything about the program. Every requirement that the program has, everything that the program is expected to do. You have to specify what it should do on every valid input. You have to specify what happens on invalid inputs. You have to predict what idiot users are going to do. And before you've even written a single line of code, you have to know how to handle it. People write books about this for their programs. And then after they've specified all the requirements for their program, then they'll go through and they'll be like, okay, well, what libraries and tools am I going to make use of? How long is it going to take me to write each and every single bit of this code? And you actually have to plan and say, okay, it's going to take me 15 minutes to write this line of code, and if I run into this particular problem, it might take me an extra half hour, and if I run into this particular problem, it's going to take me an extra 2 hours. People actually do this. There are formal standards. Not every company uses them. One of them is known as CMM. You literally have to write a great big book that plans every detail of the program down to how much time it's going to take you and how much money it's going to cost you before they actually start writing the program. We're not going to require you to do that. But we do have some requirements. And we call it in this course the design recipe. It's not an essay. Yes, it is going to be more than the number of lines of code you're going to write. But it's very important. So the design recipe is going to be with every function that you write in this course, with the exception of assignment 1. You are forgiven for assignment 1. You don't have to do it. But for everything after assignment 1, we do expect you to do it. And in general, you should get into the practice of doing it because it's good for you. Not just from the perspective of, oh yes, it's good because look at all the documentation, I could show this to a potential employer and they'll like it. No, it's good for you because it's good for you to write readable code. The design recipe is going to make it readable. So, what is in this design recipe? There are 5 components. The first component is the purpose. If you're writing a function, you should probably tell people what that function does. Now, sometimes the name of the function makes it kind of obvious what the function does. Sometimes it doesn't. If I have a function magic, I don't know what it does based on the name. So I should actually write a purpose that says the magic function does the following. And when we are writing the purpose, it's very important that we include a discussion of how the parameters to said function are actually used in that function. Because your user, and you have to assume that you are not the one that's going to be using the program you're writing. Assume it's somebody else, and assume that they are an idiot. You need to tell them in a very clear and specific language what the function does and how the parameters are used in that function. So you need a purpose. Then we need a contract. Now, a purpose, it doesn't matter what programming language you use, you should actually have a description of what this function does. The contract, on the other hand, is something that's very specific to the Racket language. What a contract does is it's going to specify the types of all of the arguments, but it also specifies the type that is of what the value that is produced by the function is. So if you look at a function like add, the parameters to add are numbers. It doesn't make sense to take a bunch of strings and add them together. Okay, yes, I know there are some languages where you can totally do that. But I can't add a brick to a chair to a number. That doesn't make sense. So a add in Racket takes 2 or more numbers, and it produces a number. That is telling me that this function is going to take numbers and produce numbers. Whereas if I have an add function for strings that concatenates one string to another, so I have hello and world and it puts them together, then I would have to specify add takes 2 strings and produces another string. The contract specifies those types. That's unique to Racket. Then you should give some examples about how to use the function. Never assume that the person using your code or looking at your code is smart. They may not be able to figure out how to use your function correctly from the purpose and contract that you've provided. So by providing some non-trivial examples, you're giving them a concrete example of how this function should be used and the type of output that they should be expecting. Now, in general, you should give at least 2 examples. And the examples for us are also going to serve as tests. Make sure that when you're doing examples that it's not something trivial like 0 and 0. It has to be a meaningful example. Something that actually shows the user what this function does. If I have a function square and I pass it 0 and it gives me 0, that doesn't tell me anything. But if I have a function square and I pass it a 2 and it produces 4, hey, I'm like, oh yeah, it squares it. Meaningful examples. Then we have the definition. So the Racket definition is part of the design recipe. Your code is part of the design recipe. And that is the header. And the header of your function is actually the part that binds the name and parameters, or the parameters to the name. So that's the little line, define, name, params. That's the header. And then the body is the actual meat and potatoes of the function. So we have the definition of the function. And then after you have the definition in your file, you would have the tests. Now we do expect you, by the way, in this course, to write your own tests. And you might be thinking, oh, so much work. Well, if you don't write any tests, then how do you know your code works? If you come into my office and you say, I don't know why this works, it doesn't work. What's wrong with it? And I look at your file, and you've got the function definition, and you have no test. I'm going to be like, well, did you test it? What did you test it on? What all did you test? And maybe you only did one test. One test isn't enough. It's never enough. If I have a function called bake me a cake, and it consumes a flavor and it produces a cake, then there are a few tests that I might want to run. Like number 1, bake me a cake, no matter what flavor I give, it should actually make a cake. Number 2, if I send bake me a cake a flavor like chocolate, then the cake that is produced should be a chocolate cake, not a pickle-flavored cake. Well, aside from that being gross, of course. Tests are very important. There's absolutely no reason for you to submit code and you don't know what's going to happen. You should have written enough tests such that you know for certain that your code works or doesn't work before you submit it. Now, I'm not telling you you shouldn't submit code that doesn't work, because obviously if you've got 5 seconds left of the deadline, submit something. Get the mercy marks. You gotta get something. But any code that you submit, you should know the state of it. You should know whether it works or not. Those tests are how you know. It's like a math proof. If you write a math proof, you know whether it's right or wrong. That's assuming you haven't done this, a bunch of hand-wavy stuff in there because you're not really sure and you're just hoping the TA gives you some I'm bored of marking marks. You know with a proof whether it's right or wrong. With the function you write, because of the tests, you should know whether it works. You should know. All right. Now there's one other reason why tests are really important. Let's suppose you write your test and your function works and you come back a week later and you're like, you know, I'd like to change the implementation out. I had this brilliant dream the other night, and my dream told me how to write this function in 2 lines instead of 5. So you go back, you change your implementation. Those tests that you wrote before serve as what we call regression tests. They're there to make sure your new implementation or your update or your modification didn't impact the correctness of your code. They're very, very useful. You are going to be graded on them. We are going to check to make sure, number 1, you have enough tests. And you might be thinking, oh, I'll just spam them with a bunch of 0 tests. No, our TAs are actually checking to make sure that you are testing all of the appropriate boundary cases. With numerical functions, it's things like, did you make sure it behaves well with 0? Did you make sure it behaves well with positive numbers? Did you make sure it behaves well with negative numbers? Maybe it's a function that takes imaginary numbers, or could take imaginaries. Did we test that? Generally speaking, we don't use imaginaries in this course, but theoretically speaking, we might. You have to test all of these things. We can't really, without having anything more than math expressions, do much testing discussion today, but next class we will start talking about some of the more interesting aspects of testing. All right. So what order do you do this in? I'm going to amend this order a little bit. It's not quite right. So they say that first you should write a draft of the purpose because yes, you have a problem, you need to start planning it on a piece of paper, or maybe planning it in the comments. So you write an initial draft of the purpose. Now I need to write a function that sums some numbers together. I don't know what I'm going to call it yet, I'll keep thinking about it. So you write your initial purpose draft, and then you're like, okay, well now let's write some examples. How do you want to actually call this function? At that point you figure, okay, I'll name the function this. Oh, it's going to need to take a few parameters, and you'll write some examples for how you want it to be used. And then, after you have some examples and a draft of the purpose, you can actually write both the contract and the header of your function. Well, now that you've actually put some stuff, some skin out there, now you can go back and amend your purpose so that it actually says, okay, function X, these parameters, does this, this, and this with those parameters. You can go back and fix it, make sure it's all nice and wordy and all of that. And then you can write the body of your function and then you write your test. Or at least that's what they say here. Okay, I'm going to change it up. Tests are not just tests. There are different kinds of tests. There are 2 distinct classifications of tests, and it is incredibly important to know the difference between them. There are black box tests and there are white box tests. And all of the tests that you've seen so far are black box tests. And all of the tests that you could do for assignment 1, yeah, those are probably black box tests too. A black box test, you do not know the implementation of the function. You know what the function is supposed to do, and you write tests based on that. So my function, bake me a cake, I don't know how the cake gets baked. I don't know if there's a bunch of Oompa Loompas making me a cake. I don't know if it's my 5-year-old in the kitchen making a mess. Don't know, don't care. I simply want to know if I call bake me a cake vanilla, that I get a vanilla cake. That's a black box test case. I know nothing about the implementation of the function in order to write those tests. Black box tests should be written before you write the function. And that's not just me telling you that. That is everybody in industry since forever. Black box tests should always be written before you actually write your code. And that way, when you're done writing your code, you run the tests and bam, you instantly know whether what you wrote works or not. Now, the other kind of test is called white box test. And a white box test, you do know the implementation of the program. And the white box test cases are specifically trying to break pieces inside the function. So once we talk about conditionals in next class, we will be able to write white box tests, which require knowledge of the implementation. That means that white box tests can only be written after after you've implemented the code. So do your black box test cases first and your white box test cases afterward. We are going to expect that you have both on assignment 2 and beyond. And by the way, I will post some sample problems probably over the weekend so that you can get some experience figuring out what tests are appropriate for certain functions. All right. So let's look at an example of this, going through it. So we've got our purpose. We start out, I want to write the sum of squares function. Takes the square of two numbers and adds them together. Yeah, it's boring. Whatever. So then in my examples, I don't write the code at first. I work out the examples on paper because you should never use your own code to produce the result that you're comparing to. Because if your code's wrong, then the test passed, except it's actually wrong. So we work out our answer on paper, and then I'm going to write my actual example here. We'll talk about what this check expect is here in a minute. So I make some examples. I recommend at least 2. And now I can go and I can write my header and my contract. My contract indicates that sum of squares consumes 2 numbers and produces a number. Right? And then I write my header. I can go back now and update that purpose. And, well, this function, technically speaking, could only actually have black box test cases. So technically, I would write those test cases before I wrote the body of the function, but of course that's not how it's done here. Write the body, and then I have my tests. That's the order that these things should actually appear in your code, by the way. Purpose, and then we've got examples, contract, definition, and the tests afterward. Now, if we put this all together, this is what sum of squares should be submitted as. Now, let's see. Our function definition, 2 lines. Total number of lines you wrote. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 80% of what you wrote for this was the documentation. And I know, for many of you, this is a very stressful thing. Because you're like, well, I got the function down, and it only took me a couple lines. But I spent 50 lines documenting it. What a waste of time. It's not a waste of time. I know it feels like it, but by doing this design recipe, you are not only communicating with others exactly what this function does and exactly how to use it, your coworkers and your friends will know, okay, I know how to use it, I know how I should expect the results to look like, and because they've given me such an extensive list of tests, I actually believe that the code they have given me works. There's nothing worse than showing up for work, somebody handing you a piece of code, and you thinking it works and it runs and it does not work. That sucks. If I give you a piece of code with an extensive list of tests, I actually have some confidence in what you've written. Give people that confidence. You're not just giving them confidence, you're giving yourself confidence. All those tests, and you know whether it works. You know. All right. Yes? How would I write the purpose of my magic function? Well, okay, so something like that magic function is a stupid function. I would probably write something to the effects of an English translation of what the math does. Yeah. Not very exciting. This is actually a good time to point out, not every function you write makes sense. These magic functions, they're stupid. They're stupid. Don't write stupid code. All right. Now the tests. I've told you already that there's a difference between them. And by the way, the difference between black and white box test cases is actually described in the slides. So if you want a formal definition, it's here for you. I think it's important to mention that earlier. So there are different ways that you can write tests. You'll notice that in our examples previously, we used this function called check expect, We want to make sure that the function, when it is applied to certain arguments, gives an expected result. And you might be like, well, why don't I just compare and check if they're equal? And that's what your textbook technically tells you to do. Don't do that. There are 3 functions that are built into Dr. Racket that we would like you to use for tests and examples. They're check expect, check within, and check error. They're actually quite useful, and I'll give you an example of using them here in a minute. So check expect is an equality comparison. And so if I have sum of squares and 25 and I use check expect, if it gives me the expected result, the test pass. And Racket will actually, Dr. Racket will actually say, yes, test passed, yeah. And if it doesn't pass, Dr. Racket would be like, yeah, you expected this and I got this. It will tell you very clearly that the test has failed. So check expect is for exact comparisons. Now here's the problem. Not every number is exact in Racket. Some numbers are truncated or rounded, inexact numbers, things that are irrational. You can't use a direct comparison for them. I can't use the equals operator. This is actually a problem in computer graphics. We know that when we're trying to test whether the arrow hits the ball, the balloon, that if the arrow just comes along tangent to the sphere due to rounding of numbers, we may get the wrong answer. So what we do is we check within a range. We have an epsilon value and we say, okay, well, if it's within epsilon of 0, then it's a hit. Otherwise, it's a miss. And for any inexact numbers or rounded numbers, you should use check within. So check within, and you have to specify that epsilon value, that you have to be within that value of the specified, or that epsilon of the specified value. That's a really, really important thing. You're probably not going to use check within very much this term. Maybe a little bit, but not too much. Now the last one is check error, and this one is pretty rare to use, but sometimes certain inputs can give us an error message. For example, if I decided that I don't like the divide operator and I actually write a divide function called divide, and we want everything to be friendly English, or whatever language you choose. So if I write a literal word divide out, and somebody passes me a denominator that is 0, my function should say that this is a division by 0 error. And if I want to check to make sure that my code gives me that division by 0 error, I can use check error to make sure the error message produced is the one that I expect it to be. It will be very rare for you to use this one. I don't think I've ever actually used it. But it's out there. Check expect is the one you're going to use the most. And if you are reading the textbook does not mention these. But this is the only way we want you to do tests. Now, let's actually do it. So we'll go over to Racket here. And let's make it full screen. Or maybe it won't work. All right. Let's make a function. Oh, Racket's frozen. That's fun. There we go. Always good when it freezes. So let's define, we're going to do a stupid function, okay? Just a really stupid function. Let's say add. I said it was a stupid function. It's just going to take 2 parameters. And let's say I was in a hurry typing, or maybe it was St. Patrick's Day and you were at the Ezra Street party. If you don't know about that, Google. And maybe you came home and you're like, oh, I'm going to write some code. And you're all tipsy and stuff, and so you accidentally write this. You're supposed to just be adding the 2 numbers together, and then you write your tests. Well, I'm going to do check expect. Now, we should have written our tests first, but this person was intoxicated when they wrote it, so. I expect if I add 1 and 1 that I get 2. And I apologize for all the extra and missing C's. My keyboard's actually broken. I need to get it fixed. I expect 0 plus 0. That should be 0. And we should check to make sure that this works with negative numbers. And, well, we should have negative numbers and positive numbers together. That's a good one, too. Right? There's 4 tests. That's actually a pretty comprehensive list of tests. And, where is it going to be in there? All right. So, we've got ones for 0. I've got ones for positive numbers. I've got ones for negative numbers. And I've got ones that have positive and negatives. So now let's actually run this piece of code. When I hit run, it actually popped up a message, and you couldn't see it here, but there it is. Oops. There it is. Test results. Ran 4 tests. Those check whatevers are actual formal tests within Dr. Racket. And that if a test fails, this window will pop up and tell you that there were test failures. And in this case, it said 0 tests passed. And then for each of the tests that didn't pass, it tells you the actual value it got from the function and the expected value. And then you would go back to your code, and you're like, oh, crap, it doesn't work. What am I going to do here? So you go over here, you're like, oh, there's an extra 1. Typo. It happens. And then you run it again. And this time, because we've corrected the function and all 4 tests pass, you get a message with simply all 4 tests pass. Great. So that is how we actually use these and the kind of outputs that you should expect from them. All right. Any questions about the check, expect, check within, check error? Okay. All right. So, on to this discussion of contracts. So a contract is something that's actually unique to Racket. And what our contract does is it's going to specify the type of each of the arguments. So if I have a function like add, the arguments to that function need to be numbers. And so my contract is going to specify that both of the arguments are numbers. And then it's going to specify what the expected type of the produced value is. So if I'm adding 2 numbers, I expect the produced value to also be a number. And so I'm going to actually write it as, and this is the format that you have, the name of the function, colon, a list of all of the parameter types, arrow to indicate produces, and then the type of the produced output. Every single function you write has to have a contract. This may seem very silly to you. A function like add, it's kind of obvious that the parameters should be numbers. But you should assume your users are idiots. You should assume that the people who are using your code are the kind of people that shove peanut butter and jelly sandwiches in VCRs. And if you think that's a very random example, it's because I have a cousin that has done that. There's one in every family, right? Now, sometimes a contract isn't enough. For example, if I have the equation of a sphere has a radius. It's the distance from the center to the surface of the sphere. Well, does it make sense for the sphere or the radius to be negative? No. The sphere should not have a negative radius. Neither should a circle. That doesn't make any sense. So if I were to write a function to, say, compute the volume of a sphere, my radius can technically be an irrational number or a rational number. It could be a real number. But you know what it can't be? It can't be negative. But I don't have a type for that. So what I'm going to do is I add a special section known as the requires section. These are additional requirements on our parameters above and beyond the type. So if I require a parameter to be greater than 0, I add a requirement section. Now you don't need a require section for every function. If your function parameters have no requirements, like add has no requirements. We should be able to add negative and positive numbers. That's fine. But let's say it was divide. I require my denominator to be greater than, not be 0. And so because there is that additional requirement, I add the requires section. So that section about requirements, that's only needed if a parameter needs a specific value. Now, on that note, I want to go back to this type section here. We differentiate between different kinds of numbers. So integers are obviously positive and negative integers. Num is what we use for real numbers. So positive and negative, rational, irrational, all of those lovely things. Nat. Nat is any number, any integer greater than or equal to 0. Now this is one of those things where you're like, but I thought nats didn't include 0. And to be fair, last week so did I. I thought whole numbers included 0 and not nats. Actually, this is a complicated issue. And if you look at the definition of a nat, some people include 0 and some people don't. We, in this course, include 0 in the natural numbers. Technically speaking, it's supposed to have a different symbol to indicate 0 is included, but we're not using symbols, we're using names. Now, when you are specifying the type in your contract, it is absolutely critical that you use the correct spelling and the correct capitalization. If you get the capitals wrong, I've seen them deduct marks. So let's say you give the type in lowercase, I've seen them deduct half a mark. There's no reason for you to lose that mark. Make sure you specify it exactly. All right. Why do we have a contract? How many of you have written a program before? In any language? Okay. For those of you who have written code before, when you had a parameter to a function, did you have to specify as part of the syntax in the language what the type was? How many of you say yes? Most of you. Did you notice that we didn't do that in Racket? Because we don't do it in Racket. Languages like C and Java and C++ and Objective-C and all those things, they're what's known as a statically typed language. When I write my code, I explicitly state exactly what all the parameters are and what the type of the return value is. So this is a little snippet of C code here. So I have an add function, and double, by the way, is, you can think of it as a real number. So when I write this function add, I specify parameter A is a double, parameter B is a double, and this function returns a double. I actually have to specify that in my code. It is statically typed. If I then, later on in my C program, call add, and I pass it 2 strings, when I compile this code, C is not evaluated like Racket, it does something else. We won't worry about what it does. But when I compile it for the computer, it won't compile. You can't even translate this into something your computer can understand because I have violated the type of the function add. It's a statically typed language. I must specify in advance what all my types are. Racket is not statically typed. It's not. I almost called it radish. Whee! All right. So Racket is a dynamically typed language. What that means is you don't specify the type. Racket, as it is evaluating, is going to figure it out on its own. And if, as it's evaluating through stepping, which is what it does, it realizes, oh, right, this parameter is the wrong type for this. During the evaluation, it will throw an error that says, oh, this is the wrong type. You've passed me something that's the wrong type. In a statically typed language, you will know that you have passed it the wrong type before you even try to run the code. In Racket, you won't know you've passed the incorrect type until the code is actually executing. Dynamically typed figures it out on the fly. There's also untyped languages as well. Now there are positive and negatives to this. Dynamically typed languages are very simple. They also tend to create very flexible code because a lot of operators can actually work on multiple types. That's really cool. Here's the downside. What if it's your cousin that put the peanut butter and jam sandwich in the VCR and he sees an add function, he's like, yeah, I'm going to pass it a string and a sandwich. How does he know that it's not supposed to take a string and a sandwich? Because the function call doesn't tell him what type it is. That's the downside of dynamic typing. It actually makes the code less readable in a way because we haven't clearly specified the types of the parameters and the return value. That's what your contract's for. That's my fault. I don't turn my ringer off because nobody has my number. It's probably the spam people saying we're going to arrest you or something. I've been getting a spam call about that like every day. Anyways, so one of the problems in Racket is because we haven't actually, it's not a statically typed language, we don't know as a user what the type the arguments are supposed to be. So the contract is there to tell us what the types should be. That's why we need it. Because if we don't have it, then how am I supposed to know that add doesn't take strings and sandwiches? Maybe it does. I don't know. It's a mystery. Contracts are absolutely critical for languages like Racket for this reason. So it's really, really, really important you do it. All right. Any questions about that? We'll be expanding on the types and stuff next class. One last thing I want to say about the contract is Racket isn't looking at your contract, by the way. That contract is actually a comment, which means it's ignored. It is literally just something for a human. So does that mean we are that the types are being enforced in Racket? Not until runtime. So yes, even though you've told the user that it must take numbers, they could still technically pass it a string and a sandwich. In this course, by the way, generally speaking, unless we specifically tell you otherwise, we're not going to give you nefarious inputs. So you don't have to assume the user is an idiot passing you strings and sandwiches for a number function, unless we tell you otherwise. And in some assignments for some questions, we may say, hey, you need to check the input for validity before you actually do anything. It will be very clearly specified in the question if you have to do that. But generally speaking, we don't have any nefarious inputs. No. That being said, if you go out and you're programming out there, whether it's for assignments because you don't want to do them yourself, you want your code to do it, or because you go work at a company, always assume the user's an idiot. Just assume it and always check. And for the record, if you're thinking that all functional languages are dynamically typed, they aren't. There are some languages like ML which are actually statically typed. So it's not all functional languages. All right. So for more information, by the way, about the style guide and all that, you can go to the course website and you can download the style guide. The first, I think, 19 pages are what you should look at. Yeah, I know it's a long read. But do you want to lose 25% of your mark because you didn't capitalize something? Let's not do that. Let's actually have the course this term have the highest grades ever. That'd be great, right? All right, so that's kind of the end of that section. So I'd like to then just start talking about Module 4, just to introduce the ideas to you. So again, this is on the course website. So what we've given you now is really simple. You've got the ability to write constants, and you've got the ability to write some basic math functions. Not that useful, actually. That's just a glorified calculator. All right. We need to start building a few more types. and conditional expressions into this, so i.e. different logic elements. So to start off with, there are other types, obviously, than numbers, and one of the most useful types, other than a number, is a Boolean. So this is either a true or a false, and we use the Boolean type to answer questions, so propositions. So if I want to know if two arguments are equal, or maybe I want to check to make sure that my user hasn't given me an argument for my denominator that's equal to 0, I would ask the question, is x equal to 0? And that question returns yes or no. Well, we're not going to use yes or no, we're going to use true and false. So there is the Boolean type, and it has only two values, true and false. And for the Boolean type, in Racket, you can just type the word true or the word false. Simple English. But if you're playing around with Dr. Racket, you're going to see a bunch of other possibilities for how you represent true and false. You may also see #T and #F, and I'm probably guilty of using these. That is Scheme's way of representing true and false. If you see that, #T is obviously true, and #F is obviously going to be false. You may also see #true and #false, which are obviously true and false as well. Do not use the format of the pound symbol followed by T or true. Use just the plain English true or false. Make your code readable. There's a lot of aspects of the Scheme language which Racket has been built upon that are very much not readable. I'll introduce some of those things to you as we go, so you understand why they made Racket instead of just using Scheme. But true and false, that's what you need. On its own, that's useless. We need the ability to actually ask these questions. And, of course, Racket has such functions built in. We have equals to check for equality between two things. We have less than, greater than, less than or equal, and greater than or equal to. And they all have the format, or most of them have the format, number produces bool. Now note in a contract that the bool is written just bool, not Boolean. Didn't want you to write all those extra characters, right? The only language I know that actually makes you write out Boolean is Java. Everybody else just uses bool. Now, in addition to the propositions for comparing two things together, we also have connective operators. So and, or, and not also exist as built-in functions in Racket. So and is going to return true if and only if all arguments evaluate to true, or evaluates to true if at least one of its arguments evaluates to true, and not flips. So if it was true, it makes it false, and if it was false, it makes it true. You have access to all three of these. Now, interestingly enough, the function and or actually take more than two parameters. So they can take any number. And we'll look at that next class. So we'll leave it there for today. You have everything you need, by the way, to do A1 and get that all completed through. And I know it's tempting to think that the Jeopardy problem needs a conditional. It doesn't. All right. I'll see y'all on, I guess, Thursday.